of scalar coupling. We discussed chemical shifts in the previous lecture. The second most important aspect of NMR spectroscopy is scalar coupling. We observed the other day that due to the chemical shift phenomenon, the same nuclei or the same isotope existing at different positions within a molecule has a characteristic LUMS frequency. That was the chemical shift phenomenon. But if you look at the fine structure of the peak from a single spin at a particular chemical shift position, it has a finer structure. We observe that the peaks are split. There is a multiplet pattern associated with each peak, and this is what we are going to investigate very quickly today. Now, if you look at ethanol, and this is a carbon-13 spectrum of ethanol, if you forget the hydroxyl proton and assume that it is in a state of chemical exchange with solvent, there are two kinds of protons. One are the methyl protons and the other are the methylene protons, and both of them, as we know, have different chemical shifts. Now, if you look at the carbon-13 spectrum, that is, our spectrometer is tuned to detecting the LUMS frequency of carbon, we observe that there are two groups of peaks. Of course, one of these group of peaks or one of these multiplets comes from the methylene proton and the other multiplet comes from the methyl proton. And this is the peak that originates from the methyl carbon-13, and this is the group of peaks that originate from the methylene carbon-13. Now, how do we explain the fine structure of the multiplet? Now, observe that in ethanol, if you look at this carbon-13 is coupled to two protons, and both of these protons have the same chemical shift. If we are talking about isotopomers here, so there is one isotopomer in which this carbon is carbon-13, whereas this carbon is carbon-12, the natural abundance carbon. The other isotopomer is where this carbon is carbon-13 and this is carbon-12. And the least abundant of these isotopomers is when both of these carbons are carbon-13. So let's focus on the more abundant, but not the natural abundant isotopomers, in which this is a carbon-13 and this is a carbon-12. So if this were a carbon-12, there is no coupling between the two carbon nuclei because this is an NMR silent proton. But this carbon-13 nucleus is coupled to two protons. And the multiplet from this proton, from this carbon, is split up into a group of three peaks. And the intensity, the ratio of the intensities is 1 to 1. Now, I will shortly explain the origin of this multiplet pattern. Now, if you look at this carbon 13 nucleus, the other isotopomer, this is coupled to three protons. And each of these protons, of course, is NMR active. It spin 1/2. So as a result of the coupling to the three protons, the peak of this carbon-13 is split up into 4 peaks. The multiplet is a quartet. It comprises 4 peaks, and the ratio of these 4 peaks is 1 to 3 to 3 to 1. Now, how do we explain the origin of this finer structure? Any questions so far? Now, if a carbon-13 nucleus is coupled to a single proton, proton of course is NMR active, and we're looking at the carbon-13 spectrum. This carbon-13 spectrum will be split up into a doublet. And the reason is, the naive reason, I will give you a more detailed reason later, but the naive reason is that the spin state of this proton can be alpha or it can be beta. There are two orthogonal states which form the basis for this proton spin. And depending upon whether the proton is in the alpha state or in the beta state, the energy of this system can take up two different values. So a single line is split up into a doublet, and the splitting of these lines, the horizontal axis of course is the frequency axis, so the splitting of these lines has units of frequency, and this splitting is typically of the order of 100 Hz, and this is called the amount of scalar coupling between the carbon-13 and the proton. Now suppose the carbon-13 nucleus is a part of a methylene group in which there are two protons. Now both of these protons are equivalent. We will later on describe what is meant by equivalence, but we will formally describe equivalence, but naively or intuitively we know that these protons are equivalent. So as a result of the carbon-13 being coupled to the first proton, the first splitting occurs, and as a result of the carbon being coupled to the second proton, the second level of splitting occurs. So if you look at this diagram, this is the first splitting, this should be about 100 Hz, and this is the second splitting, it's another 100 Hz. And since there is no distinction between the coupling of the carbon to the proton, the first proton, and the coupling of the carbon to the second proton, the splitting should be the same. So what happens is one line occurs at this frequency, one line occurs at this frequency, and there are in fact two lines on the same position on the frequency scale that occur here. So the intensity of this peak is 2 times the intensity of this peak. So this is in fact two peaks overlapping at the same position on the frequency scale. So when you have coupling to a single proton, you get a doublet. When you have coupling to two protons, you get a triplet. And this is a spin half nucleus. Spin half की वजह से, एक spin half की वजह से दो में splitting होती है. ठीक है, यहाँ दो spins में की वजह से इस तरह का एक triplet pattern बन रहा है. और अगर हम इस बात को आगे बढ़ाएं तो in a methyl group the carbon is coupled to 3 protons, and if you look at this diagram, this is the first level of splitting, the second level of splitting, and then the third level of splitting. So the ratio is 1 to 3 to 3 to 1. So this is the quartet. So you will observe that the relative intensities of these peaks follows the Pascal's triangle, ratio 1 to 1, 1 to 2 to 1, 1 to 3 to 3 to 1. अच्छा, अगर अब आप देखिए कि जाहिर है अब ये पीक कार्बन-13 की मेथल कार्बन की वजह से है, क्योंकि it is being coupled to 3 protons. So this is the quartet, this is the triplet. अब आप ये ट्रिपलेट देखें, इसका फाइनल स्ट्रक्चर देखें. You have a triplet in the ratio of 1 to 2 to 1. But if you look at each of these lines in the triplet, it is further split up in the ratio of 1 to 2 to 2 to 1. And the reason for this is that this carbon, although the major splitting, this splitting from here to here occurs by coupling of the carbon to the metal protons, but this carbon is also coupled to the vicinal protons, that is the protons that are present 2 bond lengths away. And there are 2 kinds of those protons.
These intensities will be 1:2:2:1 or 1:2:2:2.
अब देखो ना, पहली बात तो ये जो पीक्स है ना, ये एक मल्टीप्लेट है, ये पूरा मल्टीप्लेट है, ठीक है, और इसकी ये रेशियो है 1, ये 1 है, ये 2 है, ये सारा, और ये 1 है, ठीक है. And this is because of this is the signal from the methylene carbon, ठीक है. This is the signal from the methylene carbon which is coupled to 2 protons. So when you have coupling to 2 protons, you have 1 to 2 to 1, exactly similar to this case. But if you look at each line in the multiplet, this carbon is also coupled to the 3 protons of the neighboring carbon. So if you look at the final structure of each of these lines in the triplet, it's a quartet. So you have a triplet of quartets, and this quartet is in fact the coupling of this carbon to these 3 protons. ठीक है? और आपको ये भी नजर आ रहा है कि कार्बन और हाइड्रोजन के दरमियान जो स्प्लिटिंग है, which is this difference, the difference between this peak and this peak is much larger than the coupling of this proton to the carbon, which is just this difference. So this carbon hydrogen splitting could be 130 Hertz. This carbon and hydrogen scalar coupling could be, I think, 4 or 5 Hertz. So you can have one bond coupling as well as 2 bond coupling, and you can have a range of different splitting effects. अच्छा, इसी तरह प्रोटॉन स्पेक्ट्रम अगर आप एथेनॉल का देखें, you forget about the hydroxyl proton again, you look at this proton. This proton is coupled to a carbon 13, but let's talk about the natural abundance proton, the natural abundance isotopomer. This proton is coupled through 1, 2, 3 bond couplings to 3 other protons. So this proton will have a distinct chemical shift, and it will be split up into a quartet in the ratio 1 to 3 to 3 to 1. So this quartet originates from the methylene protons, and if you consider one of these protons, because all 3 of these protons are chemically equivalent and they will have the same chemical shape, these 3 protons, each one of them will be coupled to the 2 methylene protons through 2 bond couplings. In fact, 3 bond couplings, 1, 2, 3. These are 3 bond couplings. So the proton, this proton will be coupled to the methylene proton, and since there are 2 methylene protons, you will get a triplet in the ratio of 1 to 2 to 1. And the overall intensity of this multiplet will be 3 over 2 times the intensity of this peak, because there are 3 methyl protons. ठीक है? और ये भी याद रखें कि the coupling of this proton with this proton is the same as, it's symmetric. It's the same as the coupling of this proton with this proton. So if you take 2 peaks here, look at the frequency spacing, it will be the same as the frequency spacing between 2 peaks on the other. So coupling is a totally symmetric phenomenon. अच्छा, मुख्तलिफ तरह की कपलिंग स्कीम्स हो सकती हैं कि अगर if you have an uncoupled spin, it will just give you one line. If you have a spin A which is coupled to another nucleus X, you will get a doublet. If you have A coupled to 2 identical nuclei, you will get a triplet. You can get a quartet. If you have 3 spins, A, M, and X, and the couplings are all different, so A coupled to M will give you a doublet, and A coupled to X will give you another doublet, so you will get a doublet of doublets. But all 3 spins must have distinct chemical shifts, and their couplings must be distinct. Otherwise, you get all kinds of strange effects. Now, if you have, for example, a spin half particle, such as proton, a spin half nucleus coupled to a nucleus which has spin 3/2, such as boron. Now, the direct coupling of the proton with the boron or with the 3/2 quadrupolar nucleus will give you 4 peaks, because the degeneracy of associated with spin 3/2 is 4. So you will get 4 distinct peaks. और one bond couplings की different strengths हो सकती हैं. There are different kinds of molecules I have made here, and typical coupling strengths in units of Hertz. There are 2 bond couplings have distinct strengths as well. They are generally smaller than 1 bond couplings, and the coupling can have a certain sign as well. Now, if you take a spectrum, an NMR spectrum, what coupling does is that it splits the peaks, and you can resolve the finer structure of the peaks. But since there is a large number of peaks that appear in this spectrum, your spectrum gets complicated. So, for simple first analysis, if you would like to take a carbon 13 spectrum, that is, you apply a 90-degree pulse only on the carbon 13s and turn on your acquisition, you will get a carbon 13 spectrum that is coupled with the protons. But if at the same time you apply a radio frequency to the protons at their Lambda frequency at the same time, then effectively you can decouple the two protons and the splittings will disappear. So this just simplifies the spectrum. This phenomenon is called heteronuclear decoupling. The sign of J, Lambda frequency has a certain sign, J has a certain sign, because there is a Hamiltonian associated with J, with scalar coupling, and that Hamiltonian is 2 pi J I Z S Z. Now this J can have a certain sign. So this means that if two spins are in the same direction, whether it's a lower energy configuration or it's a lower energy configuration, that the two spins are in the opposite direction. So this determines the sign of J.
decoupling हो रही है, इसमें आप फील्ड ऑफ डाइवर्जेंस आएगी, टाइम एवरेज हैमिल्टोनियन
बिल्कुल, the time average Hamiltonian does not have this coupling term. Now in decoupling, what happens is that you are applying a pulse on the proton. That is, you are randomizing or scrambling the spin polarization of proton. Now at half of the time the coupling is plus IZSZ and other half it's minus IZSZ. So on average there is no coupling Hamiltonian, and that is why the carbon appears decoupled. So exactly this is the scheme. On average there is no coupling. Okay, the concept of chemical equivalence. I hope there was some more time to discuss this, but if you look at this molecule, 1,1-difluoroethene. If you look at this molecule, the two fluorines are chemically equivalent, which means that the two fluorines, of course, they are of the same isotope, they have the same nuclei, and there is a mirror symmetry operation that can transform between the two fluorines. So the two fluorines are chemically equivalent. Agreed? They will have the same chemical shape. If you take an NMR spectrum, the Lambda frequency, this fluorine will be the same as the other fluorine. Likewise, in benzene, you have the 6 protons, and you can draw this icon for the molecule. The 6 protons, all of them have the same frequency. Water, the 2 protons have the same frequency. So the protons are chemically equivalent. You will get just one chemical shape. Now let's look at this molecule is chloroethane. Now if you look at chloroethane and you look at the Newman projection of chloroethane, you look along the carbon-carbon bond. So this is one molecular conformation. And there is rapid rotation about the carbon-carbon axis. Now if you look at the methyl group, and you consider the rotation of the methyl group about this axis, H1 is here in this staggered conformation, H1 is to the left in this staggered conformation, and H1 is at the bottom at this staggered conformation. So even though in one particular conformation, H1 and H3 don't appear to be chemically equivalent, H1 and H3 don't appear to be chemically equivalent, even though H1 and H2 do appear to be chemically equivalent. But because of this rapid change in the molecular conformation, and because of the fact that all three of these conformations have the same energy, and because of the rotation of the molecule, the rapid rotation of the methyl group, the molecule spends equal time in all three of these conformations. That is why all three of these conformations have the same probability of existence. And as a result of this rapid motion, the 3 protons in the methyl group have the same chemical shape. अच्छा, लेकिन बाज़ बात ऐसा भी हो सकता है अगर आप ये वाली मॉलिक्यूल देखें जिसमें R1, R2 और R3 डिफरेंट फंक्शनल ग्रुप्स हैं और इन दो प्रोटॉन्स को कंसीडर करें, even though R1, R2 and R3, this group is rapidly rotating about the carbon-carbon axis, and you can look at these 3 conformations. The 2 protons of the methylene, they will not be chemically equivalent, because in any one of these conformations there is no symmetry operation that can relate H and the 2 methylene protons. So even though these methylene protons are a part of a CH2 group, they are not chemically equivalent. These are called diastereotopic protons. ये पढ़ेंगे ना? पढ़ेंगे ना? So they will not have the same chemical shift. अब बात आती है मैग्नेटिक इक्विवेलेंस की. अच्छा, मैग्नेटिक इक्विवेलेंस ये कहता है, मैं इसकी एक मिसाल देता हूँ. ये 6 प्रोटॉन्स है बेंजीन के अंदर. They have the same chemical shift. They are chemically equivalent. And there is no other proton or no other spin active nucleus in the molecule in the natural abundant state to which these protons couple. So, if the protons are chemically equivalent and there are no other spins in the molecule to which coupling can occur. Similar is the case for for water. If we ignore the oxygen 17 isotope of water, there are no other spins to which these protons can couple. So not only are these spins chemically equivalent, but they are also magnetically equivalent. अब बात बाजी हो जाएगी जब मैं एक एग्जांपल आपको दूंगा. अभी देखें, ये है 1,1 डाइफ्लोरोईथीन. इसमें दोनों फ्लोरीन्स केमिकली इक्विवेलेंट है, लेकिन मैग्नेटिकली इक्विवेलेंट नहीं है. उसकी वजह ये है कि अगर इस फ्लोरीन की कपलिंग देखें इस प्रोटॉन को के साथ, तो ये सिस कपलिंग है, और अगर इस फ्लोरीन की कपलिंग देखें इस प्रोटॉन के साथ, तो ये ट्रांस कपलिंग है. So the strength of the J coupling, scalar coupling of this fluorine to this proton is something, and it's different from the coupling which is represented by this atom. So even though the two fluorines are chemically equivalent, they're not magnetically equivalent. ठीक है? So magnetic equivalence में एक तो chemical equivalence चाहिए, और उसके ऊपर उस पर एक additional शर्त ये चाहिए आपको कि the protons or the nuclei for which you are considering magnetic equivalence, they must have the same coupling to every other nucleus inside the molecule. So, but this fluorine has one kind of coupling to the proton, and this fluorine has another kind of coupling to the same proton. Therefore, these fluorines, even though they are chemically equivalent, they are not magnetically equivalent. So, they will have the same chemical shift, but they will be coupled amongst themselves as well. अगर आप बेंजीन की एग्जांपल देखें, तो ये जो 6 प्रोटॉन्स हैं, ये इनमें आपस में जो कपलिंग है वो आपको नजर नहीं आएगी इन 6 प्रोटॉन्स के दरमियान. और वाटर के अंदर आपको इस प्रोटॉन की इस प्रोटॉन के साथ कपलिंग नजर नहीं आएगी. ठीक है? अच्छा, इसी तरह अगर ये एग्जांपल देखें, 1,1 प्रोपेन 1,2 डाइईन. ठीक है? अब इसमें देखें, ये दोनों फ्लोरीन्स जाहिर है केमिकली इक्विवेलेंट है. अब इस मॉलिक्यूल का स्ट्रक्चर ऐसा है कि ये कार्बन कार्बन कार्बन, और ये जो दो प्रोटॉन्स है एक प्लेन में लाई करते हैं, फॉर एग्जांपल XY प्लेन में, और ये फ्लोरीन कार्बन बॉन्ड इट प्रोट्रूड्स आउट फ्रॉम द XY प्लेन. नाउ इफ यू लुक एट these fluorines, as you can well imagine, they are chemically equivalent. Now the question is whether they are magnetically equivalent as well. Are they?
Yes, sir.
Yes, they are. Yes, they are magnetically equivalent, because this fluorine has the same kind of coupling to this proton as the coupling of the fluorine to the other proton. ठीक है? तो this is an लेकिन मॉलिक्यूल की ज्योमेट्री आपको बता सकती है कि केमिकल और मैग्नेटिक इक्विवेलेंस के बारे में, और बहुत सी इसकी एग्जांपल्स हैं, आप मेरी प्रेजेंटेशन देख सकती हैं. विल्किंसन कैटलिस्ट की एग्जांपल है, ये मैं आपसे होमवर्क में भी पूछ सकता हूँ, आप इसके बारे में देखिए कि ये जो फॉस्फर रोडियम इज स्पिन हाफ न्यूक्लियस. ठीक है? तो अब ये दो तरह की फॉस्फरस है, एक ट्रांस है एक सिस है, और कपलिंग पैटर्न जरा इसका डिस्क्राइब करने की कोशिश कीजिए. अच्छा, एक एग्जांपल बड़ी इंटरेस्टिंग एग्जांपल है, ये क्या चीज है? डाइबोरेन है. अब देखिए, इसके अंदर दो तरह के प्रोटॉन्स हैं, एक ब्रिजिंग प्रोटॉन्स है, एक टर्मिनल प्रोटॉन्स है. अगर आप ब्रिजिंग प्रोटॉन्स को देखें, बोथ ऑफ दीस प्रोटॉन्स आर केमिकली इक्विवेलेंट एज वेल एज मैग्नेटिकली इक्विवेलेंट. नाउ दिस प्रोटॉन इज कपल्ड टू 2 बोरॉन्स. Each of the bridging protons is coupled to 2 borons. Boron is a spin 3/2 nucleus. So as a result of the first splitting, there you get 4 lines. As a result of the second level of splitting, you get additional 4 lines. As a result, you get this multiplet pattern, which is in the ratio of 1 to 2 to 3 to 4 to 3 to 2 to 1. And the terminal protons, each one of them is coupled. Since the 2 protons are magnetically equivalent, you do not see the mutual coupling between the 2 protons. So each proton is coupled, terminal proton is coupled to to a boron and you get 4 links. अब स्केलर कपलिंग का मैकेनिज्म सिर्फ ये होता है, हमने डाइपोलर कपलिंग कहा था कि दो डाइपोल्स हैं, दो मैग्नेटिक मोमेंट्स जो स्पेस के अंदर एक दूसरे के साथ इंटरैक्ट करते हैं। जिस तरह दो डाइपोल्स, दो मैग्नेट्स को आप पास पास रखें स्पेस में, वो एक दूसरे के साथ इंटरैक्ट करते हैं। स्केलर कपलिंग का मैकेनिज्म ये है कि दो प्रोटॉन्स और टू स्पिन्स इंटरैक्ट थ्रू द केमिकल बॉन्ड। So this proton talks to the electron cloud, the electron cloud talks to the proton. So this is the mechanism of scalar coupling. इसकी मज़ीद डिटेल्स हैं, आप देख सकते हैं इस प्रेजेंटेशन के अंदर। बस ये आखिरी 2 मिनट में मैं आपको बेसिक बता दूं कि मैग्नेटिक रेजोनेंस इमेजिंग कैसे काम करती है। आखिरी 3 मिनट में इंशाल्लाह फारिग होंगे। मैग्नेटिक रेजोनेंस इमेजिंग में NMR स्पेक्ट्रोस्कोपी में हम फील्ड को होमोजेनियस रखने की कोशिश करते हैं ताकि जितनी भी स्पिन्स हैं मुख्तलिफ स्लाइसेस के अंदर वो एक ही लामा फ्रीक्वेंसी को प्रोसेस करें। लेकिन MRI में हम खुद इरादी तौर पर जानबूझकर डिलिबरेटली हम फील्ड को इनहोमोजेनियस बनाते हैं। अच्छा, इसकी एग्जांपल देता हूं कि आप देखें ये एक पियानो है जिस पर हर की अपनी एक फ्रीक्वेंसी है। अब अगर आप या मैं इसके ऊपर गिर जाएं, ठीक है, बिल्कुल हॉरिजॉन्टली गिर जाएं, तो हमारा जो बॉडी वेट है वो मुख्तलिफ फ्रीक्वेंसीज वो कीज पर पड़ रहा है, ठीक है। अब ये वाला एक्सिस ले लें आप, एम्पलीट्यूड ले लें, और ये वाला एक्सिस ले लें, फ्रीक्वेंसी एक्सिस ले लें। तो अगर आप इसको प्लॉट करें एम्पलीट्यूड वर्सेस फ्रीक्वेंसी को, तो जो आपके पास ये छवि आ रही है, जो आपको शक्ल नजर आ रही है, वो दरअसल आपकी इमेज होगा, ठीक है। तो बिल्कुल MRI में भी इसी तरह अगर आप फील्ड को इनहोमोजेनियस कर दें तो इस एरिया में स्पिन एक खास लामो फ्रीक्वेंसी पे होंगी, इस एरिया में स्पिन एक खास लामो फ्रीक्वेंसी पे होंगी। तो और यहाँ पे ये एक बोतल है, ठीक है, जो साइडवेज पड़ी हुई है। तो आपको कोई इस तरह का पल्स सीक्वेंस अप्लाई करना है कि यू रिकंस्ट्रक्ट दिस इमेज। नाउ हाउ डज दैट हैपन? In MRI you have coils that can make gradient fields. Fields are inhomogeneous along the length of the sample, along the volume of the sample. So you apply a 90-degree pulse, spins start to precess, and you turn on a gradient field in the x direction, then you turn off the gradient field, and then you turn off a gradient field in the z direction and start acquiring. This is the pulse sequence, and this is called a 2D sequence. I haven't talked about 2D spectroscopy, but it works in exactly the same manner. Now what happens if this is the object we want to image, it's a planar object. This particular point recesses at a certain frequency. Now there are two axes. One is the frequency in this time interval and the other is the frequency in this time interval. And you take a two-dimensional Fourier transform. This point appears here, this point appears at another point, and you can reconstruct the entire 2D image, and you obtain a 2D Fourier transform which will result in an image. And this is what a typical image looks like. So I've been exceptionally fast. I've omitted all the blackboard derivation of scalar coupling, but I hope this is enough to give you an idea of what role scalar coupling has to play. So chemical shift and scalar coupling are the two major components of NMR. So I thank you very much for bearing with me for 7 days and tolerating my presence in your course. And I hope I've been able to communicate a little bit of the excitement and the breadth and depth of NMR. Thank you very much.